Hello and welcome to this topic, the application of chain rule, the problem of clock. The chain rule comes from the problem of differentiating a composite function. If David can type twice as fast as Mary, and Mary can type 3 times as fast as Joe, then how fast can David type compared with Joe? Now please think this problem. Kathy, do you know the answer?
Yes, Dave can type 2 times 3 equals to 6 times as fast as Joe.
That's great. Thank you, Kathy. Now consider the composite function y equals f of g of x. If we let u is g of x, we can then think of f as a function of u. Suppose that f of u changes twice as fast as u, and u equals g of x changes 3 times as fast as x. How fast is y changing? The statements y is f of u changes twice as fast as u, and u is g of x changes 3 times as fast as x can be restated as dy du equals 2 and du dx equals 3. Just as in the previous example of David, Mary, and Joe, it seems as if the rates should multiply. That is, the rate of change of y with respect to x should equal the rate of change of y with respect to u times the rate of change of u with respect to x. In other words, we can write it in this formula. This result is called the chain rule. Now let's see some examples. Example 1. There is the dial of a standard clock and it has 10 centimeter radius, and one end of an elastic string is attached to the rim at 12 and the other to the tip of the 10 centimeter minute hand. So the question is, at what rate is the string stretching at 12:15, assuming that the clock is not slowed down by this stretching? Now, who can tell me how to solve it? Jack, please.
We need to find the length of the string first, then use the derivative to find the rate. The minute hand makes 1 revolution every hour, so at t minutes after the hour, it makes an angle of pi t over 30. By the law of cosine, we will find the length of the elastic string.
Fantastic! Thank you. So, by the law of cosine, the length is s is square root of 10 squared plus 10 squared minus 2 times 10 times 10 times cosine pi t over 30. We simplify it, then we will get s is equal to 10 times square root of 2 minus 2 cosine pi t over 30. It's a compound function. According to the chain rule we have learned, the derivative of s with respect to t is the derivative of s with respect to the 2 minus 2 cosine pi t over 30, then times the 2 minus 2 cosine pi t over 30, the derivative of that with respect to t. Alright, let's read them step by step. Then we will have the derivative. So we get that at 12:15, the string is stretching at the rate of pi sine pi over 2 over 3 square root of 2 minus 2 cosine pi t over 2. and is approximately equal to 0.74 centimeter per minute. Now let's see the next example. Example 2. A clock again. The hour and minute hands of a clock are 6 and 8 inches long, respectively. So the question is, how fast are the tips of the two hands separating at 12:20? This problem is harder than the previous one, so please take 1 minute to think about it. Jordanson, could you tell the difference of the two examples?
In the first example, 1 point is fixed, but this problem, the minute and hour hand both move. We need to discuss them one by one.
Right. So the minute hand makes 1 revolution every hour. So at t minutes after noon, it makes an angle of pi t over 30 radians with the vertical. Similarly, at t minutes after noon, the hour hand makes angle of pi t over 360 with the vertical. Thus, by the law of cosines, we can get the distance between the tips of the hands. So the distance is square root of 6 squared plus 8 squared minus 2 times 6, 8 cosine pi t over 30 minus pi t over 360. Again, we can apply the chain rule. Then we take the derivative with respect to t, apply the chain rule, we have this part. So ds dt is 1 over this square root function, then times this part. All right. Then we can find how fast the tips of two hands separating at 12:20. It is the derivative of s with respect to t approximately equals to 0.38 inches per minute. All right, so that's all for this section.